Our next and our last presentation before the break is it Rami, right? Okay, Rami Drucker, machine learning software architect at CEVA. The title is very interesting to me, honestly, on a personal level, efficiently mapping AI and vision applications onto multi-core AI processors using CEVA's parallel processing framework. Obviously, the lithography progression has slowed down a bit in recent years, but you are now capable of, and will increasingly going forward be capable of, integrating a lot of cores and a lot of numbers of different types of cores onto an SoC cost effectively. But really, what's the point in doing that if they don't end up being leveraged, right? You end up with just dark silicon that's sitting there doing nothing and you're paying for it. So efficiently leveraging multiprocessing architectures is really important. It's primarily a software and a toolset task, and he'll tell you more. All right?
Sure. All right. So for those who may not be familiar with CEVA, we are an IP company, and we make AI processors for AI, neural networks, vision applications for the edge. So if we look at current generation of AI and CV applications around the areas of ADAS, for instance, drones, security cameras, we would be able to notice that they use much bigger and more complex models, as well as higher resolution images. Now that translates into a need for higher processing power. One way to scale up and fulfill this need is by applying or implementing a multi-core architecture. So in that case, the developers are left with the need to somehow allocate the workload between the different engines or cores, and that could be slightly difficult for them. So therefore, CEVA has introduced a new tool, which is in addition to the software stack that we currently have, the CDNN. CDNN stands for CEVA Deep Neural Network AI Stack, and the name of that new tool is the Architecture Planner. And in this talk, I will show how the Architecture Planner tool analyzes the network model vis-a-vis some configuration parameters, such as the L1 and L2 and DDR sizes, and decides on the best way how to distribute the workload amongst the cores or the engines. And I'll also show some demonstrations and simulation along with the results. All right. So I'll begin by introducing the new Pro-M AI processor. It's the newest member of the new Pro-M family. Basically, this is like a combined and integrated system for AI applications. It basically entails a few hardware blocks, like the MAC units blocks, the complementary activation unit for activation layers, Winograd transform, unstructured sparsity support, and also inbuilt vector processor unit, which is basically like a DSP, and that provides more flexibility in case you encounter layers that aren't or cannot be supported directly on hardware block. So this is a programmable block that we can utilize to support more layers. There is also the controller, the master controller, which governs everything and controls the runtime. And the architecture is scalable, comes in different configurations from a single engine, 2 engines, 4 engines, up to 8. This is called a cluster, and we can also accommodate a cluster of clusters, so scale up. Here we see the subsystem, which is common to all the engines. By the way, the yellow block on the right-hand side is the L1 local memory, the scratchpad memory that is dedicated for each engine. All right, so all the blocks within that engine can share the L1 memory. On the left-hand side, we see also a yellow block. This is the L2 memory, which can be shared amongst all the engines. And I'll explain later on how we use these L2 and L1 memories. So along the hardware, we also have a comprehensive AI software stack, or SDK. It basically lives within the open source realm, and I'll explain in a second, but the core or the crux of the SDK is the CDNN. Now, CDNN can be used as a standalone graph compiler and runtime framework, meaning that it gets or takes Onyx or PyTorch or TensorFlow models, compiles them and then runs them, or, and this is what we call CDNN as a front end, but there is also an option, if you wanted to use TVM or GLOW, open source graph compilers and runtime frameworks. In that case, CDNN serves as a backend, meaning the compilation and the parsing and everything is done by TVM, for instance, and then it offloads layers or subgraphs or even the entire network onto the CDNN and from there to the hardware. We also supply optimized library or optimized layers and operators libraries, as well as connectivity solution to hosts like ARM, for instance, or RISC-V via the host OS interface. So this is regarding the CDNN SDK. All right, this is a bit busy, but I will try to walk you through what we call the development flow or workflow here that we employ at CEVA. So on the top left side, it says training, but it's actually retraining. So we get pre-trained models, all right, such as Onyx, such as TensorFlow and other frameworks. But we have a tool by the name of LightML, which supports retraining on the edge, for the edge, and basically applies quantization-aware training techniques as well as sparsity to prune the network and reduce its size. So once this is done, then we move to the next stage. This is where the architecture planner tool comes into play. It does a lot of analysis on the model as well as vis-a-vis the available memory and also other parameters, and basically spits out what I would call an execution recipe, which is how to divide the workload between the cores and the engines, at what sequence, at what order, and that recipe flows then to the third step. By the way, these are all offline steps, right? So we aren't yet running or doing any inference. This is all offline. And the last step is the graph compiler, which takes the model, takes all the information from the architecture planner and creates the output or the result of that phase is a binary file by the name, internally we call it QData. Although it's a binary file, it's not an executable file. The CEVA approach is that this file contains only metadata, right? Only information that is going to be required by the runtime engine to execute the network. I think this approach has benefits, and we'll see it shortly, because you can run multiple networks on the same instance of CDNN runtime if you have multiple cores. If we had like executable code inside the binary, this wouldn't have been possible at all. All right. Now we talked about the challenges on how to divide the workload between cores and engines. So the architecture planner tool supports several methods or parallel processing paradigms, as we call them, and we'll go one by one. So the first one is also the most common one, which is partitioning by tiles. Namely, each engine gets its own tile. but the weights are shared. I mean, this is applicable when we actually look for a feature, the same feature, but in different areas of the input feature map. So we can save bandwidth by sharing the weights. So this is the most common method for distributing the workload. Second one is a variant of the first one, but all the engines process the same tile, but with different weights. This is when we are looking for different features in the same area of the input feature. The next paradigm or method is partitioning by subgraphs. I will show you some examples of network models that inherently look suitable for this kind of partitioning, and I will also show you or simulate the algorithms to show you the results. The next one is pipeline partitioning, which is suitable if you have like type of network models such as, let's say, mobile net, V1 or V2, which are actually practically one long thread of layers. So the way to execute layers in parallel is by way of pipeline partitioning. Batch partitioning, all layers execute the same network model, but different images, like multiple sensors at the same time. And lastly, partitioning by networks. Each engine can execute a different network model. Right. So this is a very high-level illustration of the partitioning by tiles method. So as you may see, we have L2 memory, which is common and shared by the 4 engines here, and each engine is equipped with its own L1 memory. So what we do, we have also hierarchy between the tiles. So we have L2 tiles, which we also call internally macro tiles. They are bigger. So we basically divide the input frame into macro tiles, and then each engine then creates its own L1 tiles, which are smaller. And they all run in parallel. Of course, we need overlaps. And once this is done, the respective results are then copied back to L2, and from there to DDR. So this is partitioning by tiling. I'm going to show you a few more methods. So the first one is what we call model by model, or the ability to run different networks on the same processor. Here we see each engine is assigned to a different network, but the input frame or the input image is shared. So this is partitioning by networks. Next one is the one we call batch. So all the engines run the same network model, the same network type, but with different frames, different input frames for each engine. The third one is the pipelining architecture, where if you have like a long thread of layers, you can still parallelize the execution by applying what we call a pipeline. So you divide the network model into sections, and then you feed the input frame. The first engine does the first part of the model, then it propagates to the next one, and then the first engine can actually start processing the next frame. So this is a pipeline. And that is the partitioning by tiles that we showed earlier. This is a sort of like a depiction of the architecture planner. So that tool that basically determines how the workload is going to be partitioned amongst the engines. In this example, we take a model on the left-hand side, plus the parameters, the number of engines, also some configuration parameters about the memories, available memories. Then the algorithm crunches, analyzes the model, and decides how to partition. In this case, it is partitioning by subgraphs, as you may see. So we use coloring just to distinguish between the cores. What you should pay attention to is that the algorithm has strong preference to run in sequences, meaning that we don't do any context switches unless it is absolutely necessary. And also the buffers between the consecutive layers are marked L1, which means we don't go out to external memory. They can run off the internal memory of the accelerator. So that is called tunneling mode in our terminology, I would say. Okay, so each sequence continues to run on the same core to the extent possible. So I would like to also show you a simulation of how this algorithm might work. So we have a graph here, right? A network model with A is input, U is the output node, and for each node we have a cost function that illustrates or represents the load or the cycles it takes to execute. Okay, so this is the cost, and of course we have multiple paths from A to U, and we would like to actually apply parallel execution here and minimize idle time of the cores. In this example, we will use 3 cores, okay? So what we do, we use a technique that is called, in this case, breadth first. We divide the network into slices. They are numbered 1, 2, like that, horizontally. And then the algorithm decides what to do. So the first layer is A. It will be assigned to the green core, okay? And you can see in the table there, start time is 0 and finish time is 4 because the cost is 4, okay? Moving on to the second slice, right? We have 3 layers. We have also 3 cores, another problem. We can continue and assign, but the way we assign, as you see, so N is assigned to the green, B to the red, C to the yellow, and we can see that the green one, N, will finish at timestamp 14, 11, and 9 respectively. We move on to the next slice, but here we have 4 layers, but we only have 3 cores, okay? So basically we are assigning the first one that becomes available, okay? So the yellow gets F and D, and if we move on, it goes like that. Table is created until we until we reach the final node, and if we look at the results, so the last layer or the last DSP to finish is the green one at 47. So this is, as you can see, node U, so 47 cycles. But if you ran on a single inference, that would be the sum of all the costs of all the layers. It will come to 111. So there is some savings here. We also ran a true example on Inception v3. Now, if you look at Inception v3, you would see, I mean, that there is potential for parallel execution by way of subgraph distribution. This is an output of the first phase of the architecture planner. You see that no buffers are allocated. It's what I call L1 or virtual memory. And then this is the outcome. As you can see, the algorithm has preference to work in sequences to be more efficient. So we took also some measurements. As you can see on the left-hand side, this is the result with 1 core. 2 cores, we can see significant improvement. But then with 3 and 4, only marginal improvement. And that is probably because, as you could see, Sometimes the other DSPs or cores remain idle because the network structure does not allow to utilize them very efficiently. But these are the results, at least for 2 cores. We do see a significant improvement. The last paradigm I would like to show is the pipeline paradigm. So as I said, I mean, it's a bit not very intuitive, but this is the time domain, the vertical axis. And as we can see, we have 3 frames, we have 3 cores. So we feed the first frame into the first core, which does part of the work, and then transfer the results to the second core. Now we need to make sure that the segments or the sections of the pipeline are well balanced. Otherwise, what's going to happen is that we will have idle time. So the first core finishes quite quickly, but then the second DSP has twice as much processing to do. So the first core cannot actually resume or begin the processing of the second image until the buffer is freed up. All right, and so this is an example of MobileNet v2 that we ran on the architecture planner. And these are the results for 1, 2, 3, and 4 cores respectively. So as we can see, 2, we get almost 1 to 2 improvement, and then slightly less, but still quite good. All right. So to summarize, I showed you today the new ProM AI processor and the CDNN stack, plus the ability to run parallel processing on top of the multi-core chip that we have. We presented subgraph partitioning and pipeline partitioning along the results. One thing to note is that Inception v3 results that we measured, in the pipeline approach, we got better results than the partition by subgraph, which is interesting. And of course, we would need to do further testing to corroborate the results. That concludes my presentation.
Presenter, I want to draw your attention to the mic in the center of the room for any audience questions. And I will pause politely to see if anybody moves to the microphone before I switch to mine. Okay, we've got like 5 minutes for Q&A, so if you think of one, please hop up there. I've got a couple of my own.
Sure.
So I'm going to begin this first one with a compliment. CEVA was, this is just my opinion, but one of the early visionaries and innovators in the realm of multi-sensor fusion. Mm-hmm. You, in fact, have a product line within your portfolio specifically focused on fusing the sensory data from multiple sensor modalities. Mm-hmm. So question is, it's really more of a clarification. You talked earlier in the presentation about being able to run multiple models at the same time?
Correct.
But then you went off and showed a bunch of computer vision examples.
Correct.
Those don't have to all be computer vision models that are being processed, right? You can do audio and other sensory data types?
Definitely.
Can you elaborate on that?
So yeah. Even, so basically what we do in our audio processing is we also run some networks that are audio specific to improve the audio results and perform some, tricks to improve or enhance the quality of the audio. So that is possible as well. Okay. Having said that, if you basically use what we call heterogeneous architecture, which is not like 4 identical cores, but slightly different cores, then you would be able to do even audio-specific tasks. But the same software can govern the same architecture. So it is possible.
Speaking of heterogeneous, that actually was going to be my next question. So in one of the earlier slides, he showed the varieties of different DSPs and other cores that CEVA offers. You're an IP supplier, not a chip maker, right?
Correct.
People license your IP. And it's highly likely that there may be multiple CEVA cores in an SoC design doing different things, right?
Yes.
Handling different functions.
Yeah.
But of course, you don't make host CPUs, right? You're not an x86 supplier or an ARM licensee or anything like that. It's likely that there might be a display hooked up to whatever system this SoC is going to go into. So that needs a graphics processor of some sort. An SoC supplier may have their own IP that they want to integrate into the design.
Yeah.
How do you handle that? From a optimization standpoint, from an efficiency optimization standpoint, in a heterogeneous SoC with a lot of different cores. Can they directly do it in your tool set, or can you hook into other tool sets?
Well, both. I mean, we have also support for what you would call other architectures, such as ARM, for instance, and we also have a port for RISC-V, right? So this is for the host side. And then we can hook up to other, I would say, peripherals, because we have an open AXI bus architecture, and you can basically interconnect other devices. And by way of writing the drivers to access those devices, we could control them from the same software set.
Okay. Time check. 2 minutes. No audience questions? Back to my list. You listed, I think, 4 different operating systems in one of your slides that you explicitly support today, including Android, as I recall.
Android, yeah, by way of Android Delegate.
Okay. Can you talk about more general Linux support, for example? Can you talk about operating systems that may not have been on that slide, but you also support today, as well as requests for additional operating support from developers that you're evaluating right now?
Right. So in addition to Android, we do support Linux, embedded Linux, and we also have a support for FreeRTOS. If you wanted like a multi-threaded application, quite small and free of charge, so we support that as well.
Okay. One more time check. 1 more minute. One last question. How do you, in your tool set, as you evolve it, how do you handle legacy DSP silicon architectures? How long do you continue to support them? And how do you handle future architectures that will come out from your company?
So far, we have had, I think, 3 generations of DSPs, as well as 3 generations of hardware accelerators. So we always maintain some overlap in terms of time domain between the current generation. Next one is, of course, being developed as we speak, and the previous one. So at some point in time, we actually said, all right, we're not going to develop new features for the legacy cores, but we do support our customers to this very day.
Okay.
So we fix bugs and we do things, but for a long time, we had a good overlap, and every new feature went into the legacy core and the new core together. Yeah. We kept them both alive.
And of course, it's not just CPU generation, architecture generations, it's proliferations within that architecture, right? Within each architecture, there are different numbers of cores and clusters of cores and peripherals and other things like that. And that all requires support as well.
So the software stack is highly configurable.
Okay.
Basically, we use configuration files or command line options to feed the exact configuration. So the software stack can handle a lot of variations and variants between different cores, different hardware accelerators. They have different feature sets, like the number of MAC units, memory sizes. This is all configurable. You don't need to build and rebuild the same software for different architectures.
Okay.
You can control it by way of configuration.
And with that, one more round of applause for our presenter and the excellent presentation.